All right, let's visualize some mixed models. Ah, yes, visualizing mixed models. Such a tricky thing to do. How do we begin? Good question. Well, let's just think about how regression models are visualized. So we typically use a scatter plot to visualize regression models. So we got the predictor on the x-axis and the outcome on the y-axis. So like in this plot, we've got willpower on the x-axis and PTSD on the y-axis. And we can use scatter plots to observe relationships and stuff, and that's great. Of course, your predictor variable could be categorical, like in this, where you got the north versus south battlefield, and looks just fine. And it works exactly the same, except we jittered things. If you don't know what jittering is, I will leave a link for you to figure that out. And also remember that if we're trying to visualize more than two variables at a time, we can encode that third variable using like a color or a line or a symbol, like in this plot, where we're now encoding superpowers with red versus blue-ish lines. Or we could also choose to encode it in separate panels, like in this one. So yeah, that's cool. So that's how we typically visualize models. What happens with mixed models? Well, let's find out. Let's first look at a data set. So this is just part of the data set. I don't have all the rows, nor do I have all the columns. But in this data set, we've got math ACH, which is short for math achievement, which is our outcome. And then we got a predictor, which is socioeconomic status, and our cluster variable is school. So that's the school ID 1224, and of course there's lots more schools. I'm just showing the first couple of rows. Now when you look at this data set, your intuition might say, hey, why don't we just visualize like a regular model? Why do we need to complicate things? So maybe you use code like this: Flexplot, math, achievement, tilde, SES, given school. And if we were to run that, we see something like this. What? Yeah, that's kind of weird. It lumped a bunch of schools together. Like, what the heck is happening? Well, if you are smart, and maybe if you're dumb too, you'll be able to figure this out. Although if you don't figure it out, maybe you're still smart. Anyway, you'll notice that it is treating school as a actual number. So it's like in the leftmost plot, you have schools 1224 through 3688. So it's treating those as if they are values on a continuous scale, when that's not at all what they are. These are categorical variables. They are not numeric variables. Even though they have a number attached to them, they are definitely categorical. Or in other words, they are nominal. They're not even ordinal. So they're certainly not ratio or interval numbers. So you might be thinking,
all right, I'll just convert it to a factor. Wouldn't that fix things?
I don't know, let's find out. So we might take math and then mutate it if we were using tidyverse. And then we might say school is equal to factor school. Or in other words, we're just converting school to a factor. And then if we were to run this, don't do it, by the way, but if you were to run this, what would you find? In all likelihood, your computer might crash. And if it doesn't crash, it's going to take a long time to produce that plot, and it's going to be a completely meaningless plot that looks like this. What the heck is going on here? It's really hard to tell, actually. Let me explain what's going on by kind of simplifying the visual, and you'll see exactly what's happening. In this code, I'm doing the same thing I did before, where I'm converting school to a factor, but I'm also randomly sampling 3 different schools. Technically, it's not a random sample. I just picked 3. The numbers don't matter. I'm just trying to sample 3 schools at which schools I sample doesn't really matter. It just doesn't matter. Doesn't matter. And if we were then to write that same code as we had before, but now with the Math 3 data set, we would get something that looks like this. And notice that what it has done is it has given a separate panel for every school. And because we only gave it 3 schools, it gives us 3 panels. So when we tried to run that code before and we had 160 schools, it was producing a plot with 160 panels. Yikes, that's a lot of panels. And that's why it either crashed your computer or made a really nonsensical plot. So yeah, it's kind of tricky to handle the cluster variable in mixed models. But we can use this strategy where we sample just a small number to visualize those. But we could also do something else. We might visualize the different schools using colors, lines, and symbols. And so here's some code where I'm doing the same thing I did before. Again, it's necessary to convert it to a factor. And this time I'm going SES plus school, because that's how you tell Flexplot how to do separate colors, lines, and symbols. And I'm also adding that last bit of code that is basically telling Flexplot, or ggplot really, to remove the legend. And the reason why is because if there's 160 schools, it's going to give different symbols for 160 different things in the legend, and that's just going to muddy things up. We don't really need the legend. And if we were to do that, we would get something that looks like this. And That looks like confetti, doesn't it? Just all sorts of colors, and it makes sense. You're asking it to give a different color for every school, so lots and lots of different colors, lots and lots of lines, and it's really hard to tell what's going on. Kind of. You can get an idea of how the slopes are kind of sort of looking across the different clusters, but you have no idea whether those slopes actually fit the data, because it's going to be really, really hard to connect the specific color of purple, for example, with the specific line of purple that corresponds to a specific school. It's just going to be impossible to see it because there's so much overlap. So in some ways, visualizing with lines, colors, and symbols is kind of useless because we cannot evaluate how well the model fits the data. There's just too many different colors. It's going to be really hard to find the one color that matches the dots to the lines. But using different symbols, lines, and colors is useful for another purpose. What we can do is we can look back at that plot again and say, hey, how parallel are these slopes? And there's certainly some fairly major deviations, but for the most part, they look okay. So you might do something like this to decide whether an effect should be fixed or random. But unfortunately, we now have another problem. Not now, we've always had this problem. Each line in the plot is fit separately to each cluster. Or in other words, it would be as if you took just school 1288's data, did a simple regression on just their data, and plotted their line. That's exactly what's happening across each of these clusters. But we know from a previous video that that's not what mixed models do. What they do is they bias the individual cluster slope toward the fixed effect. And so the visual representations we've seen so far aren't going to really reflect what the mixed model's doing. So that's the problem. Yeah, these individual cluster lines, they're not the actual mixed model cluster level lines. Not the same. And that's mighty disappointing. But there's also another problem, and that problem is that these plots do not show the fixed effects. And arguably, the fixed effects are the most important effects in a mixed model. So, yeah, we need something else. So let me just do like a review orientation sort of thing. So yeah, when we are visualizing mixed models, we must treat the cluster variable as a factor, because it is factor, or a categorical variable. And we can use lines, colors, and symbols to look at the different regression lines in one big confetti sort of plot, but you can't see how well the model actually fits the individual data points. And instead you can do paneling, but if you try to panel on all the clusters and you have a fairly large number of clusters, like we do in this case where it was 160, it's going to take a long time to plot that, and it's going to be really hard to make sense of it because it's all going to be smushed into this small little plot. So instead, what we need to do if we're going to panel, which we should, and the reason we should is because it allows us how to see how the individual regression lines for each of the clusters fit the data. So if we're going to do that, then we're going to have to sample from the clusters and maybe only show like 3 or 4 or 5 clusters at a time. And finally, Flexplot function alone can't show fixed effects, as well as the problem that the Flexplot function is going to show biased lines for the cluster level effects. So yeah, I'm here to tell you that Flexplot will fail us.
Oh my gosh! Did he just say that Flexplot's gonna fail us? I can't believe he said that!
I didn't say that. I said the Flexplot function will fail us.
Flexplot will fail us. Flexplot will fail us.
Okay, I misspoke. What I meant to say is that the Flexplot function will not work. Instead, we use the visualize function within the Flexplot package.
Okay, you had me worried for a minute, because I was thinking that Flexplot would solve all my data analytic woes.
Yeah, it basically will, so faith in Flexplot restored, I guess. So yeah, we can't use the Flexplot function, but we can use the visualize function. So here's an example. We're going to require LME4 because that's what we used to fit mixed models. And then we're going to start by fitting a simple model looking at the socioeconomic status, both as a fixed and a random effect. And then if we were to visualize, and I'm going to say plot equals model here because I don't want the residuals just yet. I'll look at those eventually, but right now I just want to see the model. And if we were to do that, we get something that looks like this. Now, if you are following along at home, your results will probably be different than mine because what it's doing in the background is it's randomly sampling schools, and the schools that it randomly samples for me is probably going to be different than the ones that it randomly samples for you, and that's okay because it's random sampling. And by default, it shows 3 different clusters, or 3 different schools in this case. And the colored lines are the random effects, and the solid line is the fixed effect. That's a pretty cool visual, man. But what happens if you want to see more than 3 clusters? Well, I'm glad you asked. There's another argument you could add to it called sample. So if you say sample equals 20, you would get something that looks like this. And here it's starting to look a little more like confetti. But now, as opposed to the Flexplot version of this, those regression lines are the mixed model regression lines, or the cluster-specific regression lines, not some approximation like Flexplot was. And if we were to interpret this, we might say, interesting. As SES increases, math achievement tends to increase too. And although the schools have different intercepts, or their heights differ, or their math achievement score average differs, it seems that the relationship between SES and math achievement is about the same. Or in other words, we might be better off modeling this as a fixed effect, which we'll do later. Now, if you wanted to use panels instead, you could. And to do that, we're going to introduce another argument to the visualize function, which has actually always been there. And I don't remember if I taught you how to do this in the intro simplistics class, but hey, if not, you're going to learn now. Any visualize function can take a formula argument, because what it's going to do in the background is visualize is going to take a wild guess at how you want the visual to look. And there's some heuristics that it uses and some algorithm that it uses to try to figure out the best way to display that data. But if you want to have more control over it, you could always provide a formula, and this is a Flexplot style formula. So we're going to say math achievement on the y-axis, SES on the x-axis, and then vertical pipe school, or in other words, we're telling it we're going to panel on schools. And then we get something that looks like this. And we have the solid line across all the schools, which show the fixed effect. And then the kind of more transparent thin line, that is the cluster level regression line. And so we might look at this and say, hey, for the most part, it looks like the cluster level fits are fitting the data. So we probably have a good model. That's good. So that kind of gives you a basic intro of how to do this in R, but let's go ahead and jump into an R example for fun. Why not? Let's do it! All right, welcome to my R screen. This is fun. Okay, so I'm going to require LME4 and Flexplot, and let's say this is my research question, that once we control for SES, we want to know how do males and females differ in their math achievement scores. So let's go ahead and start by fitting a model. So we're going to say mod equals LMER, math achievement tilde SES plus, or sex plus SES given school. Or in other words, we're fitting sex as a fixed effect and then socioeconomic status as a random effect. And of course, we are telling it that school is our cluster variable. And if we were to do this and visualize the fit of the data, we would get something that looks like this. Maybe I'll make that a little bit bigger. And that's okay, but usually when I have a numeric variable, I want that to be on the x-axis, not the categorical variable, because right now we are artificially dichotomizing, or trichotomizing, I guess, if that's a word. We're artificially categorizing SES into low, medium, and high when we don't need to. Let's go ahead and put that on the x-axis. So, like I said, we can do that with the visualize function. So we're going to say visualize mod plot equals model, and then now we're going to add this little part that says I want math achievement on the y-axis, SES on the x-axis, and then I want schools to be paneled as well as sex. And so if I look at that, we get a plot that looks like this, and you're probably like, dude, why do we have a bunch of empty plots? Well, there are certain schools like 6578 and 7364 that were all female schools, so we don't have any male students for that school. And likewise, 2629 is an all male school, so there are no females in that school. That's what's going on there. But overall, if I'm looking at this, it looks like the model fits pretty well. The only times where it doesn't is like down here in the bottom right and the top right. So that line is not passing through the data, but we actually expect that to happen once in a while, because remember that the cluster level lines are going to be biased toward the fixed effects. So that actually makes sense. So yeah, it seems like our model's doing pretty good. Yeah. But let's run it again, because this only shows 5 schools, and I want to get a greater sample of schools. So I'm just going to go back to line 13 for me, run it again, and now it's going to look at a bunch of different schools. So, and again, I'm just looking through the data, and it seems like the regression lines are actually fitting pretty well. So yeah, I'm very comfortable that we've got a good model here. At least it seems to fit the data well. But I do want to know if we can fix the socioeconomic status slope. And so to do that, I want to visualize all these slopes together at the same time. But instead of paneling them, because it's just going to get huge, I'm going to show them as different colors. And just to make sure, I'm pretty sure it was 160. Well, I do say right there, but if you wanted to know how many clusters it was, you could do something like that. So I'm just saying unique of math $school. So that tells me how many unique values there are. Oops. Of the cluster variable. And rather than counting 151, 152, 153, I just said, you know what? I'm just going to compute the length of that. So that tells me there's 160 different clusters. So cool. And then now what I'm going to do is I'm going to do the same thing I did before, kind of, except now I'm going to put school as a different color line or symbol, which is what you do when you do the plus school. And I'm also going to say sample 160, which at that point you're not sampling anymore, you're just showing all of them, but I'm explicitly telling it to show all of them. And if I were to do that, it's going to give me this message. It says, it looks like you're trying to plot more than 6 lines, colors, and symbols. I got to give it to you. You're ambitious. Alas, I can't do that, so I'm removing the lines, colors, and symbols. I hope we can still be friends. In other words, you're asking Flexplot to give you 160 unique symbols, lines, and colors. And it's basically saying, I can't give you 160 unique symbols. I think that's where the issue actually comes in. So instead, I'm going to do the best I can. So if I were to look at this, you know what? I'm going to show you another trick. Those dots are making it a little hard for me to see the slope. So I'm going to go alpha, I think is the argument, equals 0.1. Does that do it? Yes. If you didn't know that, you know that now. Alpha stands for transparency. And so I'm making the data more transparent, and it makes it easier to see the lines. And remember, this is a model where we have allowed SES to have a different slope for each of the schools, but looking at the data, they all look really super parallel. So I don't think we need to have socioeconomic status as a random effect. We're going to fix that. And so I'm going to do that down in line 27 and 28, where I've got a fixed model where socioeconomic status is a random effect, and then a reduced model where it is not. Instead, we just have an intercept. Now remember, intercept is implied, but you don't have to put it there, so just as a reminder. And look, we're doing a full and reduced model, and we're going to do a model comparison, and I make this note here. Look, I'm jumping ahead, because that's not for like 2 more videos before we start doing model comparisons, but I'm going to show you anyway, because why not? It'll be fun. And if I were to look at the results, we would see the Bayes factor. These are interpreted exactly as they were before. So the Bayes factor is overwhelmingly favoring the reduced model. So the evidence in favor of the reduced model is 1,000 times greater than the evidence in favor of the full model. And p-value, interestingly, well, sorry. I got confused in my head. P-value is also favoring the reduced model because it's not less than 0.05. So because the 2 models are equal according to NHST procedure, we say that they are statistically indistinguishable. And then the AIC is favoring, or BIC is favoring the reduced. The AIC is also favoring the reduced. So all the metrics agree. We're going to go ahead and go with the reduced model. So now that we have the final model, I'm going to visualize the reduced model. And I'm going to add a formula, but this time I'm not going to say plot equals model because I actually want to look at the residuals. And if I do that, I get something that looks like this. And if I look at the histogram of the residuals, that looks beautifully normal. That's like gorgeous. That's like a work of art, something that you would hang on your wall. Not even your refrigerator. You would like mount and frame that and put it in your living room. That is so beautiful. And then the residual dependence plot, it's kind of wonky. You got this banding. That often happens if you have a variable that has a lower and upper minimum and maximum. So like math achievement scores can't get less than 0, and they can't get higher than 25, and so you end up getting a banding like that. Maybe someday I'll explain in more detail. I don't want to worry about that right now, though. SL plot, also they have a relatively flat line. There is a slight slope, but I'm not worried about that. So it looks like we have met the assumptions of the model. So yeah. Now we can actually, now that we're comfortable with our kind of full model, we can actually revisit our research question, which was, once we control for socioeconomic status, how do males and females differ? And so to set up that model comparison, we could do a model with sex as a predictor, and then a model without sex. That model has to live without sex. And then if we do a model dot comparison between the full and the reduced, what do we find? We find evidence overwhelmingly in favor of the full model according to Bayes factor, p-value, BIC, and AIC. So yes, we always want our models with sex. All right. And then now we are finally at the point where we can visualize the full model. So we know what our model is. We know that the full model is the best model. And so if we look at that, we can now, and I'm saying math achievement tilde sex. You're probably like, hey, why are you ignoring SES? I'm ignoring SES because that's what our research question is asking us. Our research question says, what happens if we control for SES? That's kind of another way of putting that is ignoring SES. So we are trying to say, what is the effect of SES if we just kind of ignore, we're trying to see what the effect of sex is after we ignore SES. And if we look at our plot, we see something like this. It's a very small effect. So it looks like about 12.5 for the males, and then, I don't know, maybe 12 for the females, but we could actually do estimates full, and that'll give us the exact values. And again, I'm jumping ahead here, but that's okay. So sex male. Okay, so the intercept here is going to be the female scores. So the female scored on average 12.09-ish points, and then the males scored 1.19-ish points higher. So whatever 12.09 plus 1.19 would be, that would be the male score. So yeah, that's what's happening. So to answer our research question, once we control for SES, it seems that males do slightly better than females. So even though we had like a statistically significant and we had the Bayes factor overwhelmingly favoring the full model, because the sample size is so large, it's really not all that impressive. It's not that impressive. The size isn't that big, but it certainly is there. That's what that's saying. It's only like a 1 point something difference between the two, but with such a large sample size, it's there. It's there, people. So with that, you know what I'm feeling? I'm feeling like we should, you know what I'm feeling? I'm feeling we should review our learning objectives. It'd be nice if I could see that without messing up. Learning objective number 1, why IDs should be factors. Remember, if they are treated as numeric variables, it's going to lump a bunch together, and it's going to treat it as if it's a continuous variable. And like the ID of 75 is going to be higher in ID-ness than 70, which doesn't make sense. They are categorical variables. Also, what happens when we plot all the IDs as different colors, lines, and symbols? Remember that it's just going to be confetti. So you're not going to be able to see how well the model fits, but you can judge how parallel the lines are. So there is some advantage there. And number 3, I guess, the limitations of viewing the cluster variable in panels. So with that, you're probably going to have to sample the clusters. Otherwise, you're going to get a massive plot with lots and lots of clusters, and you won't be able to see anything. Number 4, why we should not use Flexplot function for mixed models. Again, Flexplot function, not Flexplot package. We should not use the Flexplot function because it's going to have a biased representation of the actual mixed model line. So the cluster level slopes are not going to be the same as the mixed model slopes, because the mixed model slopes are going to bias them toward the fixed effect. And also the Flexplot function will not show fixed effects. So don't use the Flexplot function. Instead, learning objective number 5. Instead, you should be using the visualize function. Number 6, or whatever number I'm on, how to increase the number of clusters sampled. Remember, to do that, we just use within the visualize function, sample equals, and then whatever number you want to sample. Next learning objective, whatever number we're on, how to customize the display of variables using visualize. And remember, to do that, we just say formula equals and then specify a Flexplot formula to control exactly how the visuals are displayed. Number 800 or whatever. Pros and cons of plotting the cluster variable using lines, colors, and symbols versus panels. So with lines, colors, and symbols, you could look at all the regression lines at once for all the clusters. It's going to look like confetti, but you're going to be able to see at least the individual lines, and then you can judge whether those lines are parallel. Problem is that you can't see the individual data points, so you don't know how well the model is fitting. And instead, we can use panels, and panels are great because they show us how well the model is fitting at the cluster level. But unfortunately, you can only view a couple of clusters at a time. But that's okay. So instead, you should just sample a couple clusters and make sure it seems to be fitting. And then finally, I totally jumped ahead on the last learning objective. My last learning objective is why we should plot multiple plots. And I just told you the answer, because if you're sampling, you're only going to see a few at a time, and we want to make sure that we get as much of a view of the entire data set as we can. So plot it multiple times, make sure that there's a consistent pattern of the cluster level regression lines fitting at the cluster level. All right. So yeah, that's it. As a reminder, if you are not watching this video as part of my mixed models course, what are you doing with your life? Like, why are you not joining my class? Like, do you even want to be here? If you're just watching this on my YouTube channel, welcome. If you want to take a class from me about mixed models, please visit my website, simplistics.net, where you can choose one of two options. One, to do a self-guided course where you have access to my Canvas course that shows you the exact order of videos to watch, and it gives you quizzes and discussion boards, and you can interact with me typingly via typing, as well as interact with other people and stuff. Or the second type of class is to do a live class with me, where you get to interact with me via Zoom for 2 hours every week. You get all the same advantages of the self-guided, but you get to talk to me and ask me questions and that sort of thing. So, and we get to practice problems together and have fun and drink a beer together. Digitally speaking, metaphorically speaking. Yeah, that's what I'm trying to say. Anyway, hey, thank you for being an attentive audience, as far as I know. See you next time. Peace out.